So can the online people hear me? Can you hear me from online? 你试着 Hi class. Sorry that we have to spend some time setting up things here, because this classroom has a problem of connecting external devices with the screens here. So we are kind of similar to Hogwarts. Like each classroom has its own unique characteristic. So the previous room has some issues with recording the screen with Echo 360, and this one has some problem of connecting the external laptops with the projector here. So, but anyways, let's get started. So this time we are prepared. We are not caught off guard, so we can set things up earlier in this classroom. So, okay, let's get started. In our last lecture, we have learned the basics of functional testing, and we have learned two types of functional testing techniques. And the basic idea of doing functional testing is to somehow find partitions for the input space, because we are testing the software as a black box, so we have an infinite input space for us to choose the test cases from. So that's why we need to somehow partition the test input space and try to select representative test inputs as test cases. And similarly, we are for the two testing techniques we are going to learn today, they are also about how do we partition the input space. So the first one we are going to learn today is about decision table-based testing. The second one is kind of related to the first one. It is called cause-effect graphing. And after we have learned all these four different techniques, we will provide a guideline and some comparisons of these techniques we have learned. So for this first, let's jump into some kind of boring definition of decision tables. So basically, decision table-based testing is to first build a decision table that can capture the actions we take and their relevant effects for the program. So this is why it is called decision table-based testing. And it is considered to be more rigorous than the previous techniques we have learned, because the decision tables can enforce logical rigor, and we will learn about why it can enforce such kind of logical rigor later. And normally, a decision table has four portions: the step portion, the entry portion, the condition portion, and the action portion. So the basic idea is to see how different actions we take how different actions are taken by the program under different sets of conditions provided by the user. So you can consider these conditions are kind of the test cases we are going to have, and the actions are somehow like how do we group the program behaviors according for equivalence class. So the actions are actually like the outputs of the program. So according to this according to this definition here, we can group the decision table into 4 portions, and normally this is how we represent a decision table. So first we have the step portion, which is denoted with the thicker border small squares, and the stubs could be considered as table headers. So they are not the actual content of the table. So they are basically the headers of the table. And the entry portions are actually where we hold the actual or concrete data. So you can see that these are denoted as with the squares with thinner lines, borders. And then we have condition portion. Conditions are like the inputs from the user. So the conditions are denoted with the yellow color, and we also have action portion, which are the outputs of the program. So each one of them is like is called a portion because it's not a single cell of the table. It represents multiple cells, and we will see a concrete example later using these annotations. So a column in each entry portion, like I just mentioned, is a pair of a set of conditions and a set of actions. So basically, it is called a rule. So each rule is a pair of, you can consider it as a pair of inputs and outputs. So, and the input is represented by a condition entry, and the output of the program is represented by an action entry. So basically, rules are like the indicators of which actions are taken by the program under which conditions. So let's have a look at an example decision table with the annotations we had just defined. So you can see that on the left-hand side we have the step portion, which is represented by the rectangles with thicker borders. So basically, the steps are like the table headings. So, for example, on the upper side of the step portion, we can have 3 different conditions, and on the lower part of the step portion, we have 4 different actions. So the conditions are like the inputs, the actions are like the outputs. And on the right-hand side, we can see that we have a set of entry columns here, and each rule is represented by a set of conditions and the corresponding actions taken by the program. So this is what we can observe from this decision table. And there are 2 variations of decision tables. So in this example here, it is considered as a limited entry decision table because all the conditions here can take only binary values where each condition could be either true or false. So you can imagine the conditions as whether, for example, parameter x is smaller than 10 or not, so it's either true or false. So this is limited entry decision tables. And there are some cases where each condition can take multiple different values rather than just true and false. So, and these tables are called extended entry decision tables. And you don't need to get worried about all these different definitions here. We will learn them with some examples later. And you may notice that there are, just now we mentioned each column in the entry portion corresponds to a rule. But in this table, we can see that there are two rules, sometimes two rules could be put into one column here. So this is because of the hyphen symbol here. And actually this hyphen symbol means don't care. So it means that whenever these two conditions of C1 and C2 are determined, we don't need to care about the condition of C3 for the program to make the action of A4. So there are some conditions because it depends on how we design the conditions, and there are some cases where when some of the conditions are fixed, then we don't need to consider the rest of them. So we can put the hyphen here, don't care. We don't care about that condition. And in this case, because this value could be both true and false, so it actually corresponds to two rules. So one of them is true, 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 false, true. The other one is true, false, false. So each hyphen actually doubles the rule count. So the number of rules needed for each decision table is actually determined by the number of conditions we have, because we are building test cases according to the combinations or permutations of different conditions. And for the limited entry decision tables, so each one of the conditions could be either true and false, true or false. So assume that we have n conditions. So can you calculate how many rules do we need for the limited entry decision table? How many rules? Yes, 2 to the power of n rules. So this is actually quite accurate here. We are not using how many columns do we have, right? How many rows do we have? So we need 2 to the power of n rows for limited entry decision tables. And like I just mentioned, according to the definition, this is how we develop test cases according to a given decision table. We just use conditions as inputs and consider the actions as outputs of the program. So in this case, it is still about how we do partitioning for the input and output space. So for equivalence class, we are actually grouping inputs according to the outputs, right? Outputs of the program. And for boundary values, we are grouping the input space according to some boundary values of the inputs. So, and here we are actually considering both the potential conditions that could be taken by the inputs and the potential actions that could be outputted by the program. So we are considering both inputs and outputs to do the partitioning of the input space here. And let's use a concrete example to go through how decision table works. So let's reconsider the triangle program, where the program accepts 3 integers a, b, and c, and each one of the integer is taken as a side of a triangle, and then the output of the program will be the shape of the program, the shape of the triangle, or if these 3 integers cannot form a triangle, it will just output not a triangle. And for simplicity here, let's just ignore the range limits of a, b, and c, and so we don't care about this, and we only care about how because decision table is more about the logical relations between inputs and outputs. So here, let's just ignore the range limits we have set in our previous example in the previous slides. We just care about how potentially the inputs could affect the outputs here to design the conditions and actions. So we just care about the length relations. In this case, we just need to care about the length relations among different sides. So first, let's try to consider, this is a decision table here. And whenever we are trying to build a decision table, let's start from the easiest part, which is the action that could be taken by the actions of the program. So can you imagine what are the actions steps here? What could be described by as the actions here? Like, I won't ask you how many actions do we have, because you can just count it here. Like, we have 5 actions, but what are the 5 actions? Like, we have 4 outputs, right? But why do we have 5 actions? So obviously we can use the 4 different types of outputs as 4 actions for this program to take. And the last one is called impossible. And this is because actually in many cases, in many scenarios, we may encounter contradictory conditions which could never be satisfied. So that's why we need an extra action called impossible here. And we will see an example soon. And for the conditions, we just need to care about the relations between different sides of the triangle. The first one could be whether A is smaller than B plus C, and this is related to whether these sides could form a triangle or not. And similarly, we can have whether B is smaller than A plus C or not. And similarly, we can also have whether C is smaller than A plus B or not. And that's about whether the sides can form a triangle or not. And about the shape of the triangle, it depends on whether some certain sides are equal to each other, right? So in this case, we can design the conditions as whether A could equal to B or not, whether A could be equal to C or not, whether B could be equal to C or not. And that's how the conditions we can have for the inputs. And let's try to create some concrete rules according to the true and false combinations of these conditions. So first, assume that A is smaller than B plus C is false. Then we don't need to care about all the rest of the conditions. Do you know why? Like, the hyphens here means that we don't need to care, don't care, right? So, because if A is larger than or equal to B plus C, then the action is already determined. So it's not a triangle. So no matter how we change the rest of the conditions, it's not a triangle. So that's why we don't care about the rest of them, and it's just we can just ignore the rest of the conditions here. And similarly for B, if we set C1 to be true, and if we take the false value for C2, then we don't need to care about the rest of them and just output the not triangle output. And similarly for C3, we can also have this. And the next one could be all of the C1, C2, and C3 are true. And let's assume that all C4 and C until C6 are also true. So in this case, what is the output here? What is the action here? Yes, equilateral. So because all the sides are equal to each other, so that's why the actual action is A4. And then let's change one of them to be false. Assume that we turn C6 to be false. return C6 to be false. So what would be the condition here? What's the condition here? Condition 3? It's actually condition 5, impossible. That's because if A equals to B and A equals to C, how can we have not equal to C, right? Because they are both equal. They are both equal to A, so they should be equal. So that's why we could have some impossible actions here. So this is an example of impossible action, because in real world cases, most of the time it's inevitable that we have conflicting conditions. So that's why we need to have an impossible action most of the time. And similarly, we have, if we just turn one of these values to be false, it is an impossible case. And if two conditions from C4 to C6 are false, then it is isosceles. Yes, and this one should also be impossible, right? Because only one of the condition is false. And similarly, if two conditions are false from C4 to C6, it's an isosceles. Similarly here, and if all of them are false, then it's just scaling. So this is how we can build test cases systematically with a decision table. And this decision table is a limited entry decision table because each of the conditions here can only be true or false. Now let's consider the test cases we could have from this decision table. So do you still remember why each row count is like this, represented by each column here? This one is 32 because we have 5 hyphens and 2 to the power of 5 is 32. And this one similarly is 2 to the power of 4. This one is 2 to the power of 3. So in the end, we can have, in total, we should have 64 rules, right? Because we have 6 conditions, and we should have 2 to the power of 6 rules. And because this, one way of counting the number of test cases is to just count the number of columns here we can have. And a quicker way of doing this is to use 64 to minus 33 minus 16 minus 8, and that is 8, and use 8 to plus 3 here. So that's 11 cases. So we can have 11 test cases out of this decision table. And note that all these, for these impossible cases in real life, for these impossible cases, we cannot build corresponding test cases in real life. So in the end, we may only have 8 test cases for an actual program. And let's consider another example to show you how decision table-based testing works. And this example is the next date program. So actually, this example will demonstrate why decision tables can capture the logical relations between inputs and outputs. So the next date program, it takes 3 different variables: the month, day, and year, and it returns the date of the next day as output. And let's assume the year range is like this. So what conditions can we have out of the description of this function here? So in our last lecture, when we do boundary value testing, or when we do equivalence class testing, these are the conditions we have. We have month is in between 1 and 12, day is in between 1 and 31, year is in between this range. Sorry, there's this small inconsistency here. So but let's just use this one here. So these are the conditions here, but as you can see, they are somehow connected, or they have some relations between each other. Like, for example, the number of days, the range of days is actually determined by the months we use, right? Some months could have 31 days, some months could have 30 days, and for February we could have either 28 days or 29 days. So, and the number of days of February is also depending on the year, right? So whether if a year is a leap year, then the February could have 29 days, and if a year is not a leap year, it can only have 28 days. So this actually, these conditions here are not rigorous enough to capture the logic in between each the months, day, and years. So this is not very ideal to test out the behaviors of the program comprehensively. So what we can have instead is to break the conditions into some more detailed ones or smaller ones. So for example, we can have 3 different types of months. So the first one is a set of months where each month can have 30 days. The second one is where a set of months where each month can have 31 days. And third one is February. And similar for days, we can have the conditions where day is in between 1 and 28. We can have the condition where day equals to 29. And we can have days where day equal to 30. And the condition where day equals to 31. And for years, we can have year is a leap year or year is not a leap year. So these are the conditions we can have to capture the logic, the detailed logic between day, year, and month. So what are the actions we can have? So let's not consider the actual very concrete, detailed step taken by the program. Let's just consider the output of the program. So we can have 2 different actions. The first one is still impossible, because if a month has 30 days and it is February and it falls into D1, then it's contradictory, right? So it's impossible. And the second one is the program just accepts the input and tries to calculate the next date. So these are the 2 actions we can get. So let's think about how many conditions could we actually use if we use a limited entry decision table. So where each one of the conditions can either take true or false. So how many conditions do we finally need to use here? Remember, we don't want redundancy. So how many do we need? How many conditions? So the number of rules is actually determined by the number of conditions, right? So how many conditions do we actually need if we partition the input space like this? One, two, three plus 1, 2, 3, 4, 5 plus 2. Is that the answer here or not? Actually, if we don't think about it, if we don't care about redundancy, we can just use 2 plus 4 plus 2, which is 8 conditions. However, the last one here, if if we take y1 is true, then y2 is automatically false. And if we take y2 to become true, then y1 is automatically false. So we can just use one of them here. So we only need 7 conditions, and we only need 2 to the power of 7 rows here. So that's why, we only need to use 8 conditions. So we don't need to care about, we just need to use y1, either y1 or y2 here. So this is why we need, so this is how we can reduce redundancy when we do this design. And however, this will need us to have a large number of rules if we do that. If we make the decision table like this, we can further refine the design of this decision table. Remember, just now when we were trying to consider the action of the program, we only consider whether the program can take impossible or just accepts the input. We doesn't really care about the actual concrete action or the actual concrete step taken by the program to calculate the next state, right? We just checked whether the program accepts the input or not. So if we consider how the program processes the data, we can have more detailed actions. And with only 2 actions, we are already having 2 to the power of 6. We are already having 2 to the power of 6, to the power of 8. 2 to the power of 8 test cases or rules. And if we do this, we may need to refine the conditions and have more test cases or rules to be used. And if we change the condition, we also need to think about the corresponding actions. If we change the actions, we also need to think about the actual conditions that could cause these actions. So we may also need to update the actions here. And remember, this program or this technique is only used for black box testing. We don't really know what is the actual implementation of the program. So these actions are actually based on our guesses. So we guess that the program needs to increment the number of days. We guess that whenever the day goes beyond the limit of 1 month, we need to reset the number of days and increase the number of months. So this is only because we are doing black box testing. The actions are only determined by our guesses here. And since we have changed the actions to reflect more, to represent more details, we need to also update the corresponding conditions in order for them to reflect the changes of the actions we have taken. So for example, the changes here are like this. So we need to think about whether, because we are thinking whether the program will increment day, month, or year. So we need to think about last day, last month, and last year. So in addition to the original conditions here, what we have is we need to consider whether the month is the last month of the year, or whether the day is the last day of a month, because 28 could be the last day of February. So we make it an individual condition here. And for the leap year check, we can keep it as it is. So you can see that we are actually introducing 2 more rules. And we are already having 2 to the power of 8 rules. And if we do these, we may have more rules and in the end more test cases. So as I just mentioned, we need to consider the last month of a year. We need to consider the last day of year, and we are having two more conditions if we want to further refine our design of the decision table to capture more detailed behaviors of the program. So in this case, let's consider that although we are building more test cases, although if we still use true or false, which means that if we still use true or false, which means that whether M1 could be true or false, M2 could be either true or false, then we are having too many rules. So we can further refine this using the extended decision table representation, which means that each of the conditions here can take not only true or false, but it can select from one of the conditions here. So for example, from the predefined labels. So for example, for C1, instead of having M1 equals to true or false, M2 equals to true or false, M3 equals to true or false, instead of having that, we can have whether M, a month, belongs to M1, M2, or M3, or M4. So this is extended decision table. So you can see the entries are not just true or false. They could be the labels from what we have defined just now. So it is similar for days and years. So in this case, we can actually save the number of rules or test cases and make the design clearer. And let's consider how the new design could affect the test cases we have built and how could they cover different behaviors of the program. So for example, for the first 3 test cases, C1 is where the month has 30 days and all the days are smaller than 29. So it means that we only need to increase the number of days here, right? So they are corresponding to the same action here. So these 3 rules. And for the rule number 4, so when the month has 30 days and the day is 30, and if we calculate the next day, what do we need to do here? What actions are taken here? So that month has 30 days and we are on day 30 and we want to calculate the next day. What do we need to do? So we need to reset the day, right? Because we are going to the next month. So and increase month. So we reset date and increase month. So as you can see here, each set of conditions could cause multiple actions to be taken because we are considering a more fine-grained definition of actions here, not just whether the program will accept to calculate the next date or not. So we can take 2 actions here. And let's consider if M1 is, if the month has 30 days and the day is on the 31st day. So what is the action here? In this case, rule number 5. Yes, that's impossible because that month has 30 days. We can't be on day 31 for that month, so it's impossible. And for the rest of them, they are all the same. We just need to increase if the number of days, if the date is smaller than the number of days in that month, we just need to do that. And for the last row here in this table, so if that month has 31 days and it is not December, and And we are on the 31st day, so what should we do? We should reset day first, right? Then we should increase months. So that's how we can do. But is that all for this decision table? Are we finished with this table? Yes, we are far from finishing this table. You can see that we are not even considering the years here. So if we continue the design of this table, we can further expand it to have the second half. And instead of going through all the details here, let's consider this number 15 rule. So what are the corresponding actions that could be taken if we use this test case here? So what behaviors of the program will be triggered? Like the month is in December, and we are on the 31st day of December. So what will be done by the program? Or what actions will be taken? 3 actions? Yes, 3, 5, and 6. Yes, 3, 5, and 6. So in this case, we are, although we don't know what is the actual implementation of the program, but we can design more test cases that could comprehensively and systematically cover the potential behaviors of the program. So this is, and you can also see that how each condition the logic of each condition, how each condition is related to each particular action could be captured by this decision table here. So that is why decision table is considered as more rigorous than boundary value testing and equivalence class-based testing. However, although this table is refined, is better than the previous one, it is still not the best because it has some redundancies. As you can see here, all these conditions, they are having the same effect, right? Because for example, when M3 is, we are dealing with December here with all these conditions, and M3 D1 is, because D1 and D3, D1, D2, and D3, they are all used for dealing with February, the month of February. And M3 is unique for December. And if we have permutations or combinations between M3 and D1 until D3, we are kind of having some redundancies here because these dates are only used for dealing with the February case, and we are fixing the month to be December here. So we have redundancies here, and it is similar for this M4 here. So we have some redundancies. So what we can do is we can further merge the actions that could be taken by the month, day, and year. So we can further merge the columns here. So instead of having M1, M1D1, M1D2, M1D3, we can merge them together to make the decision table look better. So this is the final decision table we can have from the previous one. So you can see that we can merge different conditions in order to reduce redundancies. And that actually covers decision table testing. And before we jump into the next topic, let's have a 5 minutes break. All right, let's start our second half. So this cause effect graphing is actually not another technique for creating test cases. Instead, it is related to how we build decision tables, and it's actually how in early days, but it is actually how in early days computer scientists build decision tables, because in early days the programs are not like the softwares we have right now. They are like hardware, so it is actually a hardware testing technique which leads to the modern design of decision table based testing. But we are still learning it because it can somehow help us to understand why decision tables can capture the logical relations between causes and effects, or the conditions and actions. So let's continue to this. So this page is full of definitions and is quite overwhelming here. So basically the basic idea of cause-effect graphing is to only consider the desired external behavior of a program, and that desired external behavior is called effect, and cause is actually somehow corresponding to the conditions we have or the inputs from the users. So the steps of doing this cause-effect graphing-based testing is to identify the input conditions or the causes first and the actions, and then we can develop a cause-effect graph, and then we can convert or transform this graph into a decision table, and then we can convert decision table rules into test cases like what we have just done. So the difference here, as you can see from decision table, is that instead of after identifying the conditions and actions, instead of building a decision table directly, we develop a cause-effect graph first. And this graph can actually help us to understand how these causes are linked to the effects. So you can see that it is not yet another testing strategy or technique. It is just an aid for creating decision tables or representing the program behaviors. So as we are talking about graphs, we need to know about the basic components of a graph and what are the notations of these basic components. So remember, I just mentioned it is cause-effect graph is actually adopted from hardware testings, and hardware has logic gates, and logic gates are like AND or XOR, different kind of gates, or NOT gates. So this is one of the type of notations. As you can see here, this image is actually from a textbook, and you can see it's very old school style textures here. So it's actually a very old technique, and this is one of the notations here. So basically, this C1 to E1 means C1 can cause E1. So condition 1 or cause 1 can cause effect 1. And C1 not E1 means not C1 can cause E1. And these C1, C2, C3, or E1 means either one of them can cause E1. And the last one means both C1 and C2 must be satisfied in order to have E1. And this is not the only notation that could be used. So this is from another textbook, and you can see that they are slightly different, but they are still having the same basic components. So these are corresponding to logic gates in hardware actually. So basically the OR AND gate, NOT gate, OR gate or XOR gate. So XOR means either one of them could be true, but not all of them can be true. So this is XOR. So that's the basic notations of cause effect graph. And let's have a look at an example to see how it works and how it can help us to capture the behaviors of the programs. So let's reconsider the triangle program, where the three integers are taken as the input of this function here. And we can have, and similar to how we design the decision tables, these are the 6 conditions we can have. So x is smaller than y plus z, y, similarly we can have y, z smaller than the other two, and we can have equality relations among these different sides. So basically we have these 6 conditions here. And for the effects, we can also have all the 5 effects we already have. And this is the example cause effect graph given by the textbook. However, it is not very rigorous. It omitted some links. It is not accurate, and it doesn't use cause 6. So let's see why it is correct. Which part of this cause effect graph is correct, and which part of the cause effect graph is wrong, according to our understanding of this example here. So let's focus on the effects here. So let's start from effect 1. So in this link here means, so either C1, C2, or C3, either one of them, not and plus a not will cause E1, which means that either one of them is, which means that not all of them is satisfied will cause E1. Is this correct or not? Not all C1 to C3 are satisfied will cause E1. It is correct, yes, it is actually correct. And let's consider the situation of E2. It means that all of them, either one of them is correct, and C4 is not correct, which means that x is not equal to y. So it will give us a scaling triangle, which means that not every side is equal to each other. Are these conditions enough to give us a scaling triangle? So if this C1, C2, and C3 are satisfied, means that it is a triangle, right? It is a triangle. And x is not equal to y, because C4, you can see, is considered to a not. C4 is not correct. Is this enough to give us a scaling triangle? No, right? So it's actually missing C6. It's actually missing C6. So y shouldn't equal to z, right? Because only x is not equal to y is not enough. We should have more than 2 sides not equal to each other to make sure that it's a scaling triangle. And let's consider E3 here. So C4 is satisfied, which means that x is equal to y. And C5 is not satisfied, which means that x is not equal to z. So is this enough to say that this is an isosceles triangle? So x is equal to y, and y is not equal to z. This is actually still not enough. We need to make sure that it is a triangle. So we need to have the conditions about C1 and C3. So it's missing a link here. It's missing a link here. So it is similar for E4. We are missing the link for, because here, in what was given by this, example here, it only checks C5 is true, X is equal to Z is true, but it is not enough, right? X is equal to Z doesn't mean Y is also equal to Z, which doesn't give us an equilateral triangle. So we must make sure that all the sides are equal to each other. So that's why we still need C4 here. So there's another missing link in this graph. And for the last one, there's another error. So let's take a look. So E5 means impossible, and not C5 obviously is not enough for having not obvious, right? We should also have a contradictory condition for C5 to make sure that the final effect is impossible. So we can use C4 in this case as the contradictory, and C4 and also C6 as together as the contradictory conditions to cause the final effect to be impossible. So as we just saw, the cause-effect graph looks quite tedious if we want to make it correct and comprehensive. And even textbooks can make mistakes, and a lot of mistakes actually in this graph. But why do we need this thing here? So why do we still need this concept? Is it just because it's part of the history of how we develop strategies and techniques? So actually there are two reasons for us to use cause-effect graph. The first one is it can help us to actually track the logic links among inputs and outputs, which can actually help us with debugging the program. So in the end, after we do testing, what we want is we want to do debugging, right? It's not finished once if we just find bugs. We still need to do debugging, and we still need to fix them. And in order to fix the bugs, we need to know what causes the bug, right? We need to know the relations. So here, the cause-effect graph is actually helping us to clearly see which conditions are having what kind of effects for each one of the output here. So you can see if we track E1 here, assume this is correct. So we know that, okay, either not all of them is true, means that will give us E1 here. So this is quite clear. So for E2, it's similar. We can see that it is related to, assume that this is correct. We are not missing 6 for E2. So assume that this is correct. We can clearly see that, okay, C1, C2, and C3, and C4 are related to E2. And the relation is that either one of them should be satisfied, and not C4 should be satisfied for this. So if we use this kind of graph, we can clearly see how inputs and outputs are related to each other. So that's the first reason for us to use cause-effect graphing. And the second one is we can also track the logical links, not among inputs and outputs, but among the inputs themselves. So this can actually help us to reduce redundancies. For example, in this example here, we can know that C1, C2, and C3 are related to each other with an OR condition here. So which means that when we create test cases to violate this condition here, we only need to use one of them, to violate one of them. So we don't need to violate all of them in order to have certain conditions. So this can help us to reduce redundancy. So that's why we may still need to use cause-effect graphs although it is kind of a tedious process and it may have many errors. So this is why we still need to do it. And so far we have, before we come to the last topic of today's slides, let's have a quick recap of what we have learned for functional programming and what are the techniques we have learned. So for functional programming, as I mentioned for many times, so it is a black box testing technique, which means that we don't know what happens inside the program. What we only have are the specifications or the requirement specifications of the program, right? And the basic rationale of doing functional testing is to partition the input space. And there are many different ways for us to partition the input space. For boundary value testing, we partition the input space according to the different boundaries of the inputs. And for equivalence class-based testing, we do the partitioning of the input space according to according to the output of the program. And for decision table-based testing, we are not only considering the outputs, but we are also considering the logical relations between the input and outputs, so we can design test cases more systematically, and that's all the techniques we have learned. And cause effect graphing is just a visual. You can consider it as a visual aid for decision tables. So after we have learned all these techniques, let's have a look at how could we use them and compare them in real life, in real scenarios. And before we do the actual comparison, let's first think about the limitation of the very first technique we learned. So boundary value testing. So let's consider which condition is not suitable for boundary value testing here. So in this example, I'll leave this QR code for now if you want to scan it. You can also use the link here. So which condition is not suitable for boundary value testing? So does this make it clearer? Let's have a look at the results of this poll. So it seems that most of you can get it correctly. So the first one is not suitable for boundary value testing because it has only 2 values and we don't even have boundaries here. Like there's no boundaries between. It's just true and false, right? We don't even have mean value, we don't have max value, we don't have a normal value, so we don't have boundaries here. But for the second one here, it is put here to confuse you. So, like for months, we have actually there's a hidden there's a hidden range between these months. Like, it should be between 1 and 12, right? So we couldn't have month 0. We couldn't also have month 13. So that's why there are boundaries here for month. So this is why the second one could still be used for boundary value testing. So apart from this limitation, actually in our last lecture, one of you guys from online has actually asked a very good question. But I didn't have a chance to look at the chat in our last lecture to answer it during the lecture. So I think it's Jack. He asked whether in this example here, in the boundary value example here, the test cases we have designed doesn't cover one of the outputs, one of the potential output of the program, and that is scaling. So all the test cases are not covering the case where the function will output scaling here. So that is because that doesn't mean that this boundary value testing is not usable for testing. That is because when we do boundary value testing, we only consider the boundaries of the inputs. We are not considering the output of the function. So it is quite normal that we are missing certain behaviors of the program if we only do this boundary value testing like this here. So that is another potential limitation of boundary value testing. And let's look at this example and the limitations more systematically. So Boolean values, like what we have shown in the previous slide, Boolean and logical variables present a problem for boundary value analysis. So normally the Boolean values or the logical variables, they don't have boundaries, right? And boundary value testing or analysis actually requires each of the variable to be truly independent on each other. Otherwise, because if they have connections with each other, we are creating a lot of invalid test cases. So can you think of an example where variables are not truly independent? We have, using the examples we have used in our previous slides. Can you think of an example we were using just now? For example, the next date example. So the number of days is determined by the month, and it's also determined by whether the year is a leap year or not. So it's not always the case that each variable is truly independent to each other. And most of the times, the test cases are, not very comprehensive because when we build the test cases, we are not really considering the actual behavior of the program. We are only considering the boundaries of the inputs. So that's why we may miss a lot of interesting behaviors of the programs with the test cases built with boundary values. So these are the potential limitations. And here are some tips for using boundary value testing in real-world scenarios. So the first one is robustness testing is a good choice for testing internal variables. So this means that, robustness testing means we are trying to make some invalid or out of boundary some test cases outside the boundaries. So this is a good choice for testing internal variables. And by internal variables, the meaning is that, the meaning is like this. So for example, if we set, let's say we use C, let's take C as an example. So let's say we have a variable with one as a 1-byte integer, and let's say that when we write the program, the condition is x is smaller than 10, and let's assume this is a signed integer. So x is smaller than 10 is actually, there's actually a hidden condition here, not reflected by the condition of x smaller than 10, and that is the lower boundary of a signed integer that could be taken by the lower boundary of a signed integer that is of 1-byte length in C. So we need to consider underflow or overflow cases, and robustness testing can actually help us to capture these behaviors if we try to build out of boundary values with consideration of the actual ranges of the different data types. And the second one is we can create extreme boundary results from non-extreme input values, which is because, for example, we have let's say a program takes 2 integers as input, and it somehow, let's say the 2 integers are x and y, and let's say it takes 3 integers a, b, and c, and it calculates c divided by a minus b. So we can create a boundary value where an internal variable a minus b is 0 without using extreme boundary values for both a and b, right? So we can create extreme boundary values from non-extreme input values because it's a black box. We don't know how it is processed inside the program. So if we can guess how this program is implemented, then we can create some extreme boundary values inside the program with some non-extreme input values. So this is what we can do. And for the tips of using equivalence class testing, so the weaker form of equivalence class testing for both normal and robust are not comprehensive as the corresponding strong forms, because the weak equivalence class testing, we are not doing permutations of or combinations of different equivalence classes, right? So they're not as comprehensive, and they may miss some of the behaviors of the program. And for some for some targets, they are implemented with a strongly typed or statically typed programming language, and the input values can cause runtime errors. So it makes no sense to do some robust testing. For example, in Java is considered as a statically typed programming language. And by statically typed, it means that the type of a variable is determined at compile time, but not during runtime. So if, let's say, we create an integer variable, then that variable is always an integer in Java. We cannot reassign it as a string, right? It is statically typed. And if we, let's say, if we have a function accepting an integer as a parameter or as an input, and we supply strings as the input, as the test cases for that variable, then we may run into runtime errors captured by the Java virtual machine. So it makes no sense to create such form of invalid test cases for robustness testing, because we are not testing in that case, we are not actually testing the implementation of the program. We are testing more like we are testing the Java runtime. So that's why if for those for those programs written with strongly typed or statically typed programming languages, it's better not to use the robust equivalence class testing. And because equivalence class testing is more related to grouping the inputs according to the outputs of the potential outputs of the program, and boundary value testing is more on the input side. So we are considering the boundary values of the inputs. So they are actually complementary to each other, and we can combine them together to build a hybrid approach, to build hybrid, to consider both of them when we design test cases. And that's a useful tip. And the last one here is strong equivalence class testing, where we can do permutations of different equivalence classes. It still makes the assumption that the variables are truly independent to each other, which is similar to boundary value testing, where we have more than one variables. So this may cause some issue, because it is not the being truly independent is not a restriction for the program to be able to be tested by equivalence class testing. However, if the variables are not truly independent, we may cause some redundancies when we create strong equivalence class testing, because for strong equivalence class testing, we need to combine different equivalence classes together, and if they are not truly independent, then we are creating a lot of invalid test cases, right? Because of the internal connections of these different conditions. So we may have a lot of redundancy in the end if they are not truly independent. And for decision table testing, so decision table based testing, so these are the conditions where the decision table based testing technique is more suitable. So first, if the program has a lot of if then else logic inside, so although we don't know what's happening inside the program, we can make guesses, right? So if the program has a lot of these kind of logic, then it is more likely to be suitable for decision table based testing. And if there are logical relationships among input variables, then it could be also more suitable for decision table based testing. And of course, if there are calculations involving subsets of the input variables, then it is also more suitable. And if there are cause and effect relationships among inputs and outputs, then it's also very suitable. And the last one is actually similar to the first one. If the program has a high cyclomatic complexity, then it is also suitable for testing. And you don't need to worry about these terms. What is like a cyclomatic complexity? It is actually related to the number of branches inside a program. And we will cover the different measurements of software complexity in week 7, so you don't need to worry about it here. But it is briefly related to the number of if, else, or loops. And decision table, but there are some limitations for decision tables as well. For example, decision tables do not scale up well. We need to factor some larger tables into some smaller ones to remove redundancy. For example, in our second example we have learned today with the next date program, we can further refine the definition of conditions and actions to capture more behaviors of the program, but we are also introducing some redundancies, and we can remove the redundancies by merging some columns together. And so we have to iteratively work on decision tables to refine the definition of conditions and actions and remove redundancies during this process. And lastly, let's do a comparison between these different techniques. And these two figures are not created for a particular program, because for different programs, the conditions, the situations could be different. But generally speaking, boundary value testing boundary value analysis is the least complicated technique here. But however, it could give us the largest number of test cases. Remember, we could have the number of test cases required for strong, robust boundary value testing could be exponentially large, right? According to the number of boundaries and variables. And for decision tables, we need the least number of test cases. But however, it is considered the most sophisticated technique here. And for the effort in identifying test cases, of course, boundary value is considered to be the simplest one, and decision table is considered to be the one that requires most effort, because we need to draw the decision table, and we may need to refine the design of the table step by step. So it's all actually about trading off efficiency and effectiveness, where efficiency means how fast we can design the test cases, how fast we can do things, and effectiveness means how well we can do things. So it's like how we can trade off between how fast we can test these programs and how comprehensively we can capture the different behaviors of the program. And that's all about the main content of today's lecture, and let's continue our journey with the Python syntax. Do you need a quick recap of what we covered here for the last part? No? Okay. So let's jump into the Python syntax here. So there are actually many useful new features since Python 3.5. And the first one is the walrus operator. So sometimes we, because I'm using this Windows computer here to do this, to give this lecture, I don't have access to a local Python compiler. So this is what I can do. You can also do this with your own machine. So you can just open this onecompiler.com website, and you can select this Python interpreter here, and you can copy and paste code here to play around with it. So, and it's using Python 3.12. So all the features we have covered here are supported by this onecompiler.com. So that's it. And for the walrus operator here is denoted like this, and the reason of this, the advantage of using this operator is to make your code clearer. So it helps you to write clean code, and it actually doesn't introduce any new logic or new language feature. It's just help you to write cleaner code. So before if we don't use this operator, let's assume we have this condition here. So we have a variable, and we have a piece of data where this variable is used as a key for retrieving. So this one here is like, if the data is a dictionary, then A is a key. Then we can use this key here to store this variable here. So we need to check whether this key is inside this table, right? Before we can successfully store the data into the variable from the dictionary. We need to do this in 2 steps. So first, we need to create a variable called a here, and then we can assign a value inside this if here. However, if we don't want to, if we don't want to do this extra declaration of this variable, we can use the walrus operator. So this it is called a walrus operator because it looks like a walrus head rotated left. So you can search for it. It's actually because it's an animal like this. So you can see it's like a rotated walrus. So it's called walrus operator. So this can, if we use this here, it actually means we are declaring a new variable called a, and we then, after we have declared it, we store the value inside a, and that's it. So we are saving 1 line of code here if we want to do this. So this doesn't introduce any new logic or new feature. So this is just to save the lines of code. So it's similar here. So if we want to use the length of a here, and we want to use the number of n after assigning it to the value of length, we don't need to declare this variable explicitly here. We can just use this walrus operator here. So we don't need to declare it explicitly. So that's it. It's very straightforward and simple. However, walrus operator, because if we chain up operators as expressions in Python, there are priorities of how they are calculated, right? So for example, if we do this, 1 plus 2 times 3. So this times here is calculated first before we do the plus, right? So it's 7. So when we chain up different operators, there are priorities of how they are used for calculation. And this walrus operator has the lowest priority. So if you want to use it, you have to use it, put it into a parenthesis for safety, for the purpose of safety. So let's say if we don't have these 2 pairs of parentheses here, then this command becomes the comparison result of input and quit instead of the input value here. So because the walrus operator has the lowest priority during computation. And the reason of giving it the lowest priority is to make sure that the syntax is clearer. So we don't need, so for example, in many cases, we need to calculate a complex result and put it into a variable, right? In that case, if this walrus operator has a very high priority, then we need to put parentheses afterwards, right? Then it may introduce some redundancies in the syntax. However, if we give it the lowest priority, in most of the cases, we don't need to put parentheses anywhere. So that's why it's benefiting the syntax clarity by giving it the lowest priority for calculation. And the second useful feature after 3.5 is the pattern matching introduced in 3.10. So the syntax of Python was very tedious before 3.10. If we, like in C programming, we have switch cases, right? We have switch cases. But in Python, before 3.10, there's no switch cases. And if we want to have a switch in Python, we have to use nested if and else. So it's basically a large chunk of code if we want to do that. However, in Python 3.10, there's a new feature called matching. So the keyword is match. So you can consider this as a switch in other programming languages. But it is much more powerful than just a switch. So if we just use it like a switch in other programming languages, then what we can do is we can do some constant matching. For example, let's say if we are handling the response or the status code from an HTTP request, what we can do is we can match the status code and use different cases here to do different actions. And you can see there are some syntax here. So this underscore symbol means it's a wildcard matcher. It means the default case in switch. It works like default in switch. So basically, if none of the previous cases can capture the pattern here, the status here, then this case is matched. This line of code is executed. So, but it is, like I just mentioned, is much more powerful than merely a switch. So we can also do type matching. So instead of just matching the value of this variable here, this switch case here, what we can do is we can also match the type of this variable. And if you think that, okay, type matching is still not powerful enough, we can also do sequence matching. So if the variable to be matched is of a sequence type, then we can match the actual value inside that sequence. Like, for example, here is a tuple, and if this so we can match the values of each element inside this sequence. We can also combine the matching between type matching and constant matching here. So we can also match the type of that variable, of that element, of each element inside the sequence. So you can see we can have a lot of, we can do a lot of things with this, right? So, and there are more syntax. If we want to assign a name for a variable that is matched, we can use the as syntax. This means that we can assign this matched result as a variable here, and we can also use the rest keyword, or we can use the asterisk to capture the rest of the elements inside a sequence. So we can, if we run this, we can observe the results. So basically, we need to do a proper indentation. Wait, this is not captured, sorry. Instead of returning, we need to do printing. So if we run this, what we can see is it does not match the pattern. What happened here? Case dictionary, because it requires a dictionary as the first input. So let's give it a dictionary. So you can see it can actually match the type here. Does not match again. Okay, anyway, let's delete this one here. Oh, it's because Y and Z is not the second here. If we delete one of that, you can see it's very strict, and we can match anything here. You can see we can validate whether a given dictionary with complex structure matches what we want or not. So this is particularly useful for validating inputs given to a function, especially when the input is given as some variables with very complex structures. So that's why it is particularly useful for parsing configurations to check whether a configuration is correctly set by the user or not. By doing this, as you can see just now, it's very strict. It's very strict. It can be used for checking the type of certain variables. It can be used for checking the values of certain variables, and we can assign variable names for the matched patterns. So we can reuse. Imagine this thing here is passed as a set of configurations or a set of a list of sightings. What we can do is we can check the validity of this sighting here. We can also extract values from the sightings. So this is very useful for parsing configurations. So this is just an example of how can we use this match syntax to do configuration validation. And here's another example of the advantage of using match. As we can see here, let's imagine we are trying to extract the first piece of data from a list, which should be a dictionary, and the key of that dictionary is prices, and the value of that prices key in that dictionary is a list, and the first element of that list is another dictionary, and which is called USD, which is a currency. And what if we don't use this pattern matching, how can we use this data safely? How can we use it safely? What we need to do is, first we need to check whether data is a non-value or not, right? And then we also need to make sure that the length of the data is larger than 0. After that, we can safely use data 0, right? So we have to have the first if here to make sure that, okay, the first element in the data is valid, at least we can use it. And then this one here, we can get the corresponding value of the prices key. However, what if the first element of data is not a dictionary, or it doesn't have the get method here? Then we cannot safely use it. We may need some extra checks here, right? We may need some extra check to make sure that prices, the first element of data can use get. So we may need an extra if condition before this one, and after that, we need to check whether the prices is same for data. it's safe to be accessed with array or list indexes. Then we need to do this check, and finally, we need to do this get again. And if we want to do it properly, we still need to check whether this element allows us to invoke the get function. So you can see it's very, very complex if we don't use match pattern. However, if we use match pattern, this is the line of code we just need. So we just need to write whatever we want to have in the end, and it will automatically handle the rest of the cases, all the invalid cases here, if it doesn't match. So this can save us a lot of code for input validation. So this pattern matching, it is very, very useful. And another new feature of Python syntax is since Python 3.6. Before Python 3.6, when we want to do format string, what we need to do is, for example, let's assume we have a variable called 9, and let's have this function here. A is, so what do we do if we want to print out the value of A? Or A maybe instead of, what we can do is we can of course do this plus A, we can put it into one string. That's very straightforward. But what if we want to do this? What if we want to print A in between these parentheses? So we may split it as multiple strings, but what we can also do is we can also use format string and use this function here. You can see it's a keyword, it's a built-in keyword. Format A. We can also do this. So A is 9. So, however, this syntax is a little bit tedious. So what we can do is we can just use the F string. So Python allows us to annotate strings with some characters, and F means it's a format string. And you can see that this syntax highlighter turns the color of these braces into a black color. It means that it's a variable here. So let's put in A there, and then it is print out. It's the same as dot format, but it's clearer. It's much clearer. And this is F string. So you may wonder, okay, how do we print out parentheses? How do we print out braces? If we do this, if we try to print out the curly braces like this, it will complain that it requires valid input. And what we can do is we can use double curly braces to escape. So in this case, we are printing out the curly braces within the F string. And there are some other types of strings like B string, which means that it's a byte valued string. But you don't need to care. Most of the time, you don't need to use that. And F string is actually giving us, is actually helping us to print out things more, always much easier. And another thing is, within F string, we can also do some formatting for the different values. For example, if we want to format the floating point number, what we can do is we can add, sorry, not Wallace, but we can add a semicolon here, and then we can do whatever, maybe .2. What we can do is we can add the sorry, it's not allowed in integer.